yesterday, and it said it was going to be in the 40s. This is not what I had in mind. Tomorrow is supposed to be 48, so maybe we'll get lucky and we won't have quite as much precipitation, but so thank you. And I'm very excited to be here to share this special evening with our partners at LZ. Before we do that, I want to let you know that Deep Talks is made possible through generous community supporters, and I want to mention who that is. RCS Construction in Rapid City, Chris Mitchell with Edward Jones and Spearfish, Crow Creek Brewing, which you've probably all enjoyed a little bit of that tonight, and then Chuck and Jolene Lichtenwallner. That is a big last name. Okay, so anyway, we're just grateful that we have those businesses supporting Deep Talks every month. Many of you know Jarrett Heiss. He is our Director of Science at SURF, and he will be introducing our speaker.
Thank you, Anne. Let me get my piece of paper here. Well, let me say from the outset that I'm honored to introduce our speaker for this evening's presentation. Dr. Alvine Kamaha is an assistant professor at the University of California, Los Angeles, and the current chair of the Institutional Board for the LUX ZEPLIN, or LZ, experiment. She earned her PhD at Queen's University in Canada, working with the SNOLAB research group, later joining the LZ collaboration, where she led the cleanliness program to control backgrounds during detector construction phase, efforts that were critical to the results you'll be hearing about this evening. Dr. Kamaha also served as the LZ Calibration Operations Coordinator, overseeing the installation and commissioning of LZ's state-of-the-art calibration systems. Systems that provide a deep understanding of the detector response and enhance the experiment's sensitivity to a wide range of signals. Dr. Kamaha's research group at UCLA is hard at work developing novel calibration sources for xenon detectors, as well as exploring new opportunities for rare physics searches beyond the standard model, enabled by LZ's enhanced sensitivity. Finally, I want to mention that Dr. Kamaha served as a co-convener for the SNOMAS Underground Facilities and Infrastructure Frontier, which was part of the U.S. National Strategic Planning exercise to identify the most important questions in high-energy physics, dark matter figuring very prominently. Let's join Dr. Kamaha as she guides us through putting together the puzzle to understand our universe with the LUX ZEPLIN experiment.
Thank you. Thank you very much, Jared, for this very generous introduction. Thank you all for being here. I'm very, very grateful to see so many of you coming, braving the weather. I remember when I was walking to the visitor center today, I thought to myself, I would be the only one here. Because if I could stay in my hotel room, I would have stayed. You know, the icy rain and the bad weather. Thank you so much for coming. So it's my pleasure to be here. It's my pleasure to be back. I used to come to lead from 2019 to 2021 when we were building the LZ experiment. So imagine coming 4 years after to talk about the amazing result from the experiment that we have put together. Thank you so much. So today I'll be talking to you about an effort that LZ scientists and many other scientists all around the world are doing, trying to put together the puzzle to understand our universe. So what I'm going to do, I'm first going to give you some introduction on the topic such that everybody can follow. I'm going to be talking to you about the dark matter case, the genesis, the evidence, and the candidate. What is it, dark matter? I'm going to talk to you about the strategy to search for dark matter. I'm going to focus on the LUX ZEPLIN, the LZ experiment. I'll be talking about the current status of the experiment and also about the big result that we announced yesterday on the webinar. At the end, I will talk about the future of LZ. So let's start. On this slide here, I don't intend you to be able to read all of it, but what I wanted to show with this first slide is that there are many, many, many evidence for dark matter in the universe. If we start from maybe 1930s where astronomers, guided by scientific curiosity, started to use their telescope to try to study the dynamic of galaxy or the dynamic of the galaxy content. Basically, you use your telescope and then you gaze at the galaxy and you are able to study, based on some luminous content, how much they rotate or how fast they rotate. They observed something very, very interesting. The first one to make that observation was Fritz Zwicky in 1933, and he observed that the mass of the galaxy, if you were to account for it based on how fast the galaxy is rotating, you will see that there is a discrepancy. So basically, the speed at which the galaxy was rotating was higher than the actual mass of the galaxy based on the visible content. So he said, well, there might be some unseen matter inside of the galaxy, but then we needed, as experimental physicists or core scientists, rigorous measurement to be able to ensure that indeed there is an unseen or invisible matter inside of the galaxy. So we have many other evidences, for instance, studying some ancient light from the Big Bang, using some technique called gravitational lensing to try to study the content of the universe. So nowadays, we have so many other evidences, and this one here, for me, is the simplest one to try to explain to this various audience. So basically, imagine that you take a telescope, and you are able to use your telescope to look at the stars inside of the galaxy. So then, those stars, you are able with your telescope to measure the speed of the stars versus the distance they are far from the center of the galaxy. So you build a curve or you build a model based on the measurement that you have had. And you have this green curve here. So now we have some theories about how the universe works, about how things work, and so forth. One of them is called Newtonian gravity, which means that as long as we have objects that have a certain mass, they tend to pull on each other because of the gravitational force or the attractive force due to the mass of object. So if you use that Newtonian gravity as theory, then you will expect that the speed of those stars, as they are distant from the center of the galaxy, will follow this yellow curve. So then you see that there is a difference between observation and measurement, and that difference between observation and measurement is what tells us with some confidence that there should be an unseen matter inside of the galaxy, because your telescope was looking at visible matter. So this shows you that there is an unseen matter within the galaxy, and it shows you even where the unseen matter is located, because the difference between the two becomes greater at the edge of the galaxy. So we know for sure that there is dark matter inside of the galaxy, and further measurement has given us the amount of dark matter to be looking for. We know that if you look at the universe content, the universe can be categorized into three. We have some dark energy in the universe that basically caused the universe to expand since the Big Bang. We have some dark matter or invisible matter or unseen matter inside of the galaxy that caused the universe to basically expand at a controlled rate. So without dark matter, the universe will be expanding even faster. And we have also normal matter or ordinary matter making up you and I. And that ordinary matter is made of atoms, and atoms tend to interact with light. That's why you can see me, I can see you, and we can see everything around us. So imagine that everything you can see is in a class called ordinary matter, and it's only 5% of the universe. Dark energy causing the expansion of the universe is about 70%, and dark matter is the rest. So if you quickly do the math, about 80% of the matter in the universe is in the form of dark matter. So it's very puzzling, right, even for non-scientists to know that everything you see in the universe is only 5%. There is way more out there that you don't know. And you start to think and then give free way to your imagination, thinking about what can there be, right? What can that unseen matter of the universe could be? What can we do with that once we detect it? And so many other questions. But more fundamentally though, because that unseen matter is such a huge component of the universe, being able to study it and understand it to some extent will help you to understand a little bit more about our universe, how it came to be, even its evolution and its fate. One time I was talking to some friend of mine, and they were telling me about, oh, Alvine, what do you think about the fate of the universe? I was reading this Wikipedia page talking about long-term fate of the universe, so billions and billions of years from now, we are going to die from extreme heat, or we are going to die from extreme cold, or there is this right middle in between. What do you think? And I was telling them that I believe, not from mere belief only, but because of the dark matter being so abundant in the universe, it will help controlling the expansion rate of the universe, and we are not going to be in this extreme cold scenario where the dark energy completely dominates the universe and expands the universe forever, such that the distance between us becomes ever and ever and ever increasing, and we find ourselves in those isolated islands. So this is a simple example to make you understand the fundamental importance of being able to study the dark matter of the universe. Now, what do we know about dark matter? What don't we know? We know for sure that it exists because we have so many evidences, like the first slide I shared with you. We know that it has some gravity because of the way the universe came to be, from small-scale structure to larger-scale structure. Basically, dark matter acted like a glue that was pulling those small-scale structures together and breeding bigger and bigger and bigger scale structure. We know it is invisible because, as I said before, atomic matter is visible. We can see. I can see you, you can see myself. But dark matter cannot be seen, so we cannot use any optical means to be able to detect dark matter. And we think that it must be stable, meaning that it hasn't decayed to produce another particle since the Big Bang. But what is unknown, though, is that we don't know actually what it's made of. For instance, I can talk about normal matter, making up you and I, structure, and so forth. I can talk about different particles of the normal matter. For instance, the photons from the light that is brightening the room right now. I can talk about neutrons and so forth. But if you ask me to talk about particles of the dark matter, I won't be able to. So what LZ is trying to do is to probe some particle candidate. We know that the dark matter interacts very, very rarely. So the interaction is very weak. It means that it makes the detection very, very hard. And we don't know what are the properties of the dark matter. What is the mass? What are the charges, and so forth. So then we look at the particles that we are familiar with. We know that they are not dark matter particles. We have many candidates beyond those particles that we have hypothesized. And our goal, like I was saying earlier on, in LZ and any other experiment looking for dark matter is to try to find out if those particles that were hypothesized to be dark matter exist, find them, and then characterize them. So one of them I will be insisting about in my talk today is this class of weakly interacting massive particles that we call WIMPs. So in the search for WIMPs, we have many, many experiments all around the world. As you can see in this map here, you can see the LZ experiment at the surf in the map. And all those experiments are using different approach to try to find dark matter. Because the question about the true nature of the missing matter of the universe is so important, we are using different approaches that are complementary to ensure that once we find it, we know for sure that we have found it with increased confidence. So one thing that people try to do is to use some colliders where they will use normal matter particles and accelerate them to high energy and collide them. So when they will collide them, the hope is that at those high energy, they will be able to produce new particles. Another approach is to try to use either telescopes or space detectors to try to find excess of normal matter particles that we know were not supposed to be there. So that excess will be an indication of dark matter being nearby and providing via some decay or via some disintegration to produce normal matter, that excess. Or the third approach is to try to look at dark matter interacting in a detector. So some pretty pictures. This is a collider. This is how it looks like. Before the talk, someone came to me and then was talking about collider physics. So yeah, in collider physics, what you do, you accelerate two beams of high energy normal matter particles and you smash them at the center of a detector, and then you try to detect the different products. In telescope experiment, you can either use some experiment from satellite missions and looking at those excess of normal matter particles, like I was saying before, or in what we do in LZ and most underground-based experiment, you try to look at dark matter coming into your detector and transferring some energy by colliding with another ordinary matter from your detector. It's basically like a pool table game where you have a pool ball colliding and then transferring some energy or transferring some speed to another ball that initially was at rest. So what we do in those type of detectors is not really to look at the collision process in itself, but we look at the energy that will be impacted. So the one that has been collided upon will recall and we produce a signature in the detector. So those signatures are very, very characteristic of an energy or a collision interaction. So we can suddenly have in the detector some flash of light that are produced. We can suddenly have in the detector some charge or electrons or ions that are produced, or we can suddenly have in the detector some heat that are produced. So in the world right now, we have about, or even more, over 30 experiments that are invested in this type of search for the recalling nuclear signature in the detector, and they use different target material. And the different target materials are because one target material can be more sensitive to a smaller energy, and then another target material can be more sensitive to a bigger energy. So what is very interesting about this search is that the collision will happen if dark matter passes through your detector and interact, but the collision can also happen if any particle of the normal matter passes through your detector and interact. However, dark matter will interact at a level that is very, very small. So it's so small that we like to describe that interaction as feeble, okay? Very, very feeble. It can interact in the level of maybe 1 time per year in your detector, while all the matter of other particles of the ordinary matter will interact at the level of 1 time per kilogram per day. So that difference makes it such a way that every other particle will be swamping your feeble dark matter signal, making the search very hard. And you may think about how hard then is the search. The analogy that I have found suited for this presentation is basically as if I have to drop like a needle in the haystack and ask you to find that needle. I'm sure most of us will say, forget it. I'm not going to find it, right? Some of us though, we can be very, very stubborn and then say we are going to find different strategies to find it. One of the strategies would be to try to reduce the size of the hay. And that's what we do in general for those different experiments looking for those type of interaction. Our strategy is to reduce the size of the hay such that the needle can be more visible. In reducing the size of the hay, we have to understand what makes up the hay. Because if you understand what makes up the hay, you can triage it and then remove it. So in dark matter search, we have 2 different types of background or particle interaction that can produce a signal that we kind of cloud the dark matter signal you are looking for. The first one is some cosmic ray. So you know at a surface like that, if you think about it, you have a shower of hadronic or a shower of particles from the upper atmosphere coming at you right now. We have about 10,000 per meter square per minute of millions, a type of particle from the cosmic ray coming at us by now. But fortunately, those type of radiation are fine at the human level. But for a dark matter detector, trying to find an event that happens less than 1 time per year, having 10,000 time particle coming through the detector per minute will be really a search that will not be successful at all. So what will we do to kind of mitigate or reduce those background is a strategy that I'll be talking about it later. The second background I want to mention is this background coming from the natural radioactivity around us. Basically, everything around us is radioactive. Myself, I am radioactive. Your favorite pet is radioactive. The food we eat is radioactive. And basically what it means is that as human beings, right, we have an average lifespan. Unfortunately, some people pass away before their lifespan, before the average, others live longer. But even for particles, right, it's the same thing. So I can pick any particle. The average lifespan can be a year, meaning that before a year, you can have some amount of that particle that has decayed. After a year, you can have some amount also that has decayed. So here I have prepared a quiz. You don't have to answer if you don't want to, but let's see if some of you will be bold enough to answer. I have on the left the natural radioactivity in food in terms of a isotope of potassium that we know is a natural occurring element. So I have the radioactivity in food, and my question for you will be, among all those different food, which one do you think is the most radioactive? Or which one will be producing the highest amount of potassium-40 per second? Okay? Every single second there will be some production of potassium-40. So which one do you think is the most radioactive? And I have myself here as a human being of 70 kilograms, although I weigh more, and I have also a cat here. If you can pick between myself and the cat, which one we have the highest radioactivity. So maybe let's take 1 minute to guess. Someone was pointing at something. Any guess? Yes? Red beans. Spinach.
Gotta be spinach. I don't like spinach.
I would have said red beans myself, or spinach, because I love you. But, surprisingly though, the dry green tea leaves is the most radioactive. It has like 600, it emits about 600 potassium-40 per kilogram per second. But the good thing though is the dry green tea leaves. It means that the tea that you infuse in water will have a lesser radioactivity, right? And the whole point of this slide is not for us to become scared of radioactivity in food, because if you look at myself, for instance, I'm producing 4,000 potassium-40 per second, right? So all those radioactivity levels are comfortable for us. And what I'm saying again is that after you have infused your green tea, it's even less radioactive. But again, for a dark matter detector, any of this will cloud the dark matter signal we are looking for. I have talked about potassium-40, but I wanted to mention another isotope that is in the ground, the soil that you work on in the park, that is very, very, very detrimental for a dark matter detector, is the radon. And that radon comes at a level of 7,000 atoms of radon per meter square per second. So escape from the ground. And imagine all that radon escaping from the ground and then filling the air. And that air, we breathe it, that air, the detector material can be exposed to it. So during LZ construction, we had all of that in mind, and then we went through a very stringent procedure to try to mitigate against all those backgrounds. So we have those challenges. If we succeed in reducing the size of the hair, we will be able to see the needle. I will be talking to you now about the strategies to reduce the size of the hair in the context of the LZ, or LUX ZEPLIN experiment. The experiment is made of about 250 scientists from different institutions. It's a very global collaboration. We have people in Australia, in Europe, in UK, everywhere. We are supported by many, many, many agencies. We are supported by the Department of the Energy, DOE, and we also have strong support from Science and Technology in UK and the Sanford Underground Research Facility here. So the experiment has a prime location, and that prime location is 1 mile underground. Just up the hill, you reach the gate, you go inside of the laboratory facility, and then you take a cache down 1 mile underground. A cache that is similar to the one behind you there. That's a replica, and then you go 1 mile underground. And the reason why we are 1 mile underground is because remember that shower of cosmic ray, right? As we go 1 mile underground, that shower gets to interact with the rock and stops before we reach the detector. Doing so, we are able to reduce that shower, mainly the millions of concern, by a level of 10 to the 7. So 10 million times we reduce that background, which is fantastic. So because that cosmic ray background is reduced, the radioactivity of the detector material and then the environment, the air, the lab rock, and everything becomes the primary concern. So I wanted first to stop here to say, they express as LZ member, on behalf of the whole collaboration, our appreciation to SURF. It has been fantastic, you know, back to from 2019 to 2021 when I was coming here, and even following throughout the operation of LZ, the support of the lab has been fantastic. What I'm showing here is a picture of how much work goes behind building an underground laboratory. So if some of you are privy to some history about SURF, it used to be a mine that was excavated for different minerals, right? Gold was one of them, the gold mine. So after you finish excavation and you want to put a world-class laboratory there, what you have to do, you have to further excavate because you have to expand. It takes space. We have huge water tanks, we have huge detectors, so we need physical space. You expand the lab, you excavate, and after you have expanded, you have to basically polish the wall to kind of trap as much as possible some of the radioactivity in the wall, and then you have to build the lab. So this is a space that LZ is occupying at SURF. After you do that, radiogenic background becomes a concern, and one of the ways to deal with them is to make your detector in an onion-like structure. Basically, the outer layers of the detector are protecting the main part of the detector, the core, where your physics happen. So we have a huge water tank to protect the core of the detector. We have some other detectors that are there mainly to flash out or to signal whenever a background that we don't want, that is not dark matter, we pass through them. And the core of the detector is right in the middle of that onion layer. So that core of the detector basically is the world's biggest time projection chamber in the world. So it took us about 1.5 years to assemble that. It has about 7 tons of ultra-pure xenon. So imagine a huge bath of liquid xenon underground, just up the hill. And we have surrounded the detector with some reflective material that will be used basically to bounce the light and direct it basically into some special detectors that will be used to capture the light. So what happens when a particle goes through LZ? When a particle goes through LZ, there will be that recalling, and that recalling will produce the signature, like we discussed before. The signature here will be flashes of light, because xenon is a natural scintillator. Whenever there is energy deposited into xenon, it will scintillate. And once the xenon scintillates, it can also have some electrons or charge that are emitted from the atom. So electrons will start to drift, and they will produce another scintillation light at the top of the detector. So then our special light detectors will help us to visualize 2 different flashes of light. A prompt scintillation light because of the natural scintillation of the xenon, and the second scintillation light because of the drifting of the electron. So we use then those 2 scintillation lights, study different features, and we are able to discriminate, or we are able to differentiate between things that can be dark matter or things that cannot be dark matter. So, like I said before, it took us 1.5 years to build the detectors, but prior to building the detectors, it took us 5 years to carefully measure the radioactivity in different materials before we assembled the detector, because we wanted to make sure that our detector does not become the main source of those different backgrounds that we cloud the signal. And when we were building it, we had a motto: no love for dust, no radon. So we built a very, very specialized clean room that even, I like to think about it like, even in my best day cleaning my house would never be clean as that clean room. The radon in the air was reduced by a higher factor. The dust in the air was reduced because we had some filtration system. So when we finished assembling the LZ detectors, we used some UV light to flash on the detector to see if we could see specks of dust. After 1.5 years, we could not see so much speck of dust because every single time when we were building it, we were controlling how much exposure to dust or exposure to radon we had. At the end of the day, we had less than 1 gram of dust accumulated on the entire world's biggest TPC. So then we brought the detector on the ground, and this is a very, very cool milestone that happened. This is Jake here. And in bringing the detector on the ground, it was in a snow day, and it was my first time seeing it. So I'm going to talk about it because I was wowed by that. Because the detector was so huge, we couldn't push the detector like that. People couldn't carry it. So what we did at that time is to use some high pressure air to lift the detector. So you blow high pressure air, it lifts the detector, and then you have people like Jake and many other engineers guiding the detector through the tight corners. It was fantastic. And when we did that, that closed basically the assembling part at the surface lab and sending the detector on the ground. It was a big day for LZ. It was back in 2021. We reached on the ground. We put the detector inside of that onion layer structure, and we started taking science data. We have been taking science data since then, starting and stopping at some point to be able to do different fixes in the detector and other operations. What I want to say here is that the background at which we are running LZ at right now is 100,000 times less than the natural radioactivity of a human being. So that's why I was saying earlier, the radioactivity that we have talked about is fine for us human beings, but for LZ, it's not, because it will cloud the dark matter signal we were looking for. So we reduce the natural radioactivity to a very, very high percentage, such that we are running it at a very, very small natural radioactivity to be able to be sensitive to dark matter. So what we did then was to start data taking. In 2022, we had some result. In 2024, we had some result. And yesterday also, we announced some world-leading result that I'm going to briefly touch on. But before I do that, I want to talk about one of my hobbies when I used to come here back in 2019, 2021. I really love the nature. And I remember the first time seeing a deer, I was like, oh, wow. Looking and then be so amazed. And I decided that I was going to count them. So every time I was coming from 2019 to 2021, I was adding to my count. So at the end of 2021, I said, I think I have counted 66 deers. I was talking to someone, and then the person said, are you sure that you're not just counting the same deer all the time, right? Like, how sure are you that you're not double counting, or triple counting even for that? So in LZ, to avoid double counting or triple counting, in general, to avoid claiming a false discovery of dark matter, what we do, we try to carefully understand how, although we have gone underground, we have that onion layer structure, we know that there will be some residual particles still coming through. So our goal, our primary goal, is to understand how those residual particles will interact with our detector and appear in our golden parameter space. It's basically as someone who was going deer hunting, will train himself to be able to study the footprint of the deers and then their hooks and things like that, to be able to differentiate between mule deer and different types of deers. So we do that in LZ, and we have a state-of-the-art system that we send different man-made radioactive sources in different space outside of LZ or inside of LZ. And at the end of the day, we have this. We have this map of the different particles interacting in our detector, where we know that particles that prefer to interact with electrons surrounding the atoms of the normal matter will be situated, and particles like dark matter that will prefer to interact with the nucleus will be situated. So with these two different responses, we know that if we remove those man-made radioactive sources and we were to collect data and see some data in this blue band, we can confidently say it's not dark matter, because dark matter will tend to be in this red band, along with particles that preferentially interact with the nucleus. So when this is done, we just map out all our background, where they are supposed to be, and so what I have on the left-hand side is basically a repeat of what I had on the previous slide, and on the right-hand side is basically numbers. Those numbers are not important. I just wanted to have it there for scientists in the room to kind of gaze at something sciencey. Okay, so now we understand our map. We can now look at the data that we are collecting, collect data and then look and then ask ourselves the ultimate question: is there WIMP? Have we found dark matter? When we are taking data, one thing that you want is the detector condition to be stable, because a stable detector condition shows that you can reproduce the result and shows that anything that will look new is indeed new. It's not due to some fluctuation. So anytime I will be showing you some science run or dark matter search run in LZ, I will always have that keyword, stable detector condition. It's very important. It has to be stable. So we took the first data set for 60 live days. We have this. On the left-hand side, you can see our data that we collected for those 60 live days in our physical parameter space, meaning the radius of the detector, and then the depth at which the event or that interaction or that energy deposition that produced that phase transition happen. And on the right-hand side, you can see the different events that we have collected in our golden parameter space. The size of the primary scintillation light in the first axis, or the prompt light, and the size of the secondary scintillation light in the y-axis. So something very important to see is that although we have gone through that campaign of 5 years to select the best radio pure material, we still had some radioactivity. So that's why from the wall of the detector, the dashed line you see here, we have so many clusters of event. But it's fine. So what we can do, we can just cut out the wall in our analysis and remain with a very pure set of data. And that's what we have here. And at the end of the day, if I was to ask you a question, have we found, or do you think LZ found WIMP back in 2022? You will just look at this parameter space and you will say no, because all your data, the black dot, appear in the band that corresponds to those events that primarily interact with the electrons. So it was not a dark matter discovery at that time, which will be true. So in 2022, we did not find dark matter, but what we did, we were able to basically come in a parameter space that scientists have agreed upon about giving result, such that we can compare, right? Because we have more than 30 scientists in this search all over the world, so we need to compare our results and be able to help each other navigate that parameter space to see which other region should we probe for that dark matter. So what you can see there is that on the x-axis, we have the different masses of the dark matter that we were looking for. On the y-axis, we have the probability of those dark matter interacting with some nucleus inside of our detector. So LZ result here in 2022 is that dashed line. That is the lowest one possible. That shows basically that everything above that black line that has a parabola shape was ruled out. So basically LZ look at dark matter with all those different masses from 10 times of the mass of the proton to about 10,000 times the mass of the proton, and then rule them out. Anything below is still possible to find dark matter. So basically, if dark matter had some interaction probability that was above this black line, we will have found it. So since we did not find it, we can confidently rule out dark matter of this given mass range interacting above this cross section. But anything below, we cannot rule it out. So that was in 2022. In 2024, we repeated our search. We took a longer data set. Instead of 60 days, it was more than 200 days. And the condition again was stable. Again, we did not find dark matter. We combined the data from 2022 with 2024. And we had, one more time, the world best result in dark matter. Basically meaning that our curve will be the lowest one in that parameter space agreed upon by scientists. So far, LZ has the lowest curve, meaning that if an experiment was to find the dark matter candidate we are looking for, LZ will be the best position experiment to find it because the curve is the lowest, and we have probed more region than any other experiment. At that time, we had a lot of newsletters that were written about us. We made a lot of press, different titles. I will give you like 1 minute to read, but one of the titles that was very simple and accurate was this title that I circled in blue, saying that the LZ experiment narrows the search for the elusive dark matter. So basically what that title says is that by LZ not finding dark matter in 2022 and 2024 is fine because we are pushing closer and closer and closer to where we can potentially find something, right? So we are, basically, it's kind of like you have a treasure map that you have divided in different sections. The more section that you are ruling out, you are getting closer and closer to narrow. You are getting closer and closer to get to a section where you can find your treasure. Or at least if you don't find it, you can basically rule out the whole map and restart somewhere else, right? So that's what LZ is doing. So what is the current status? What's new? Yesterday announcement was titled New Result from the LZ Dark Matter Experiment. I hope some of you were able to tune in to hear our fantastic result delivered by amazing colleagues. We had some media coverage, some from Surf, some from Berkeley and different universities. I have some link here. The new result, before I talk about that, I want to give you some context. Right. Going back to the analogy of the search map, we have been ruling out different sections of a field trying to find dark matter. The goal is to look everywhere, right? To not give up until you are completely probed the field. And you can do so in the dark matter parameter space in two ways. Either you keep on doing what you have been doing, like LZ has been so good at doing it, or you try to look elsewhere, and in this case, look at lighter dark matter candidate. And yesterday's result was about looking at lighter dark matter WIMP candidate, which was a new territory for LZ, and also we got some new physics phenomena as well. So to look at lighter WIMP candidate, we had to basically make sure that we were efficient enough to look in that low energy region and to be able to push that surge to that low energy regime. It has required dedicated calibration, going back again to that footprint map. It has required more dedicated calibration to be able to understand that footprint map even better. But we did it. So what you see here about our low WIMP mass result is that even in that parameter space where we tried out with our 2025 result, LZ is still world leading. So unfortunately, we still haven't found dark matter, but we are getting there, right? We are ruling out as much space as possible, and we are getting discovery ready. LZ, because of its current sensitivity, that is fantastic. It's a premier experiment, but also it's a multi-purpose experiment, meaning that we are set up to discover dark matter, or at least to find what candidate is not dark matter, but at the same time, we can do so many other signs. So you can gaze quickly at this slide, but what I want to talk about is the result that we discussed about yesterday. It's about some neutrinos from the sun that LZ was also able to report some world-leading result on it yesterday. When you think about neutrinos, they are a little bit like dark matter in the sense that they are weakly interacting. So for instance, right now, if you were to lift your thumb up like that, about 60 million neutrinos will pass through your thumbnail. But you won't feel anything because they are weakly interacting, so you just pass through. Basically, pass through without interacting. At the sensitivity that LZ is at, we can basically use the fact that we are sensitive, and we can even detect weak interaction processes to be able to measure those neutrinos. And those neutrinos come from various origins. I'm not going to talk about all of them because the science of it can be complicated, but think about all the fusion reaction that go on through the sun to be able to get the sun to emit all that light that the sun emits, right? Those fusion reactions, we have some neutrinos accompanying them. One of them I will be focusing on is called boron 8 neutrino. And those boron 8 neutrinos, at the sensitivity that LZ is at, we can measure them. And by measuring them, we don't have to take another set of data. So we use the same data in which we were looking for dark matter, low mass, to look also for those boron 8 neutrinos. And by doing that, if we were able to measure them, it will give us a chance to glean at the solar interior and understand a little bit more about those fusion processes in the sun. So you see that it will be really an endeavor to try to understand our universe better. So some history of solar neutrinos at SURF. LZ is not the first experiment hosted at SURF to have studied solar neutrinos. We have an experiment by Ray Davis back in, I think, 1980-something, that used like a huge tank of some cleaning material. I'm trying to remember the name, I don't remember, but it was a chlorine-rich liquid. He used it to try to measure different neutrinos from the sun. And he was able at that time to measure some neutrinos, and I'm going to call the name of the neutrino, but it may not make sense. That's fine. We can discuss about it in the Q&A period. But he was able to measure the amount of electron neutrinos coming from the sun. And being the great scientist, he thought about the amount of electron neutrinos that those solar fusion processes, if you understand them well, will predict. And then he saw that there was a huge discrepancy between the amount that he measured and the amount that was predicted. So he said, well, I think there is an anomaly here. So either all those fusion processes are not correct, so they are mismodeled, misunderstood, something is wrong with them, or neutrinos may change their flavor as they are traveling from the sun, which is very far away from the Earth. And he was right, because many years after, some scientists from different labs one of them is SNOLAB in Canada, another one is in Japan, discovered that neutrinos were actually changing flavor as they were traveling from the sun to the earth, or from the atmosphere to the earth. So Ray Davis got the Nobel Prize in 2002 for his discovery, and at the corner right is a picture of Ray Davis taking a bath inside of the cavern where LZ is located. I believe that the bath was not in the detector material itself. I believe it was water. During the decommissioning phase of the experiment, it took a bath there to celebrate and things like that. So today, LZ is hosted in the Ray Davis cavern, and I like to think about it might be a good luck for LZ, right? Ray Davis got a Nobel Prize in 2002 for the discovery of neutrinos. Us being hosted there, we might get also the Nobel Prize at some point for the discovery of dark matter. Let's see. But going back to the solar neutrino, what is new though is that those solar neutrinos that were measured by Ray Davis use some processes. LZ solar neutrino use a different process. And the process that LZ used to detect those solar neutrinos is a process that normally you also use in dark matter, where you assume that when a particle interacts with the xenon nuclei in LZ, it interacts with the xenon nuclei as a whole. It does not distinguish between what type of nucleons are there and so forth. So it's kind of like a coherent or a global type of interaction. And even there, that type of interaction was already measured by different experiments, but it was using a different source. It was not using the sun as the source of those solar neutrinos. I think in 2024, 2 experiments that are LZ-like, but in different places, in Gran Sasso in Italy and somewhere in China, discover, well, measured to some extent, those solar neutrinos using the same process as LZ just did. But in physics, we have kind of a threshold for what we call a discovery, and when you are below that threshold, we call it an indication for a potential discovery, and above that threshold, we can call it a discovery or discovery-like. So those 2 experiments had some indication because they were below a certain threshold, and results from LZ were more significant because LZ is more sensitive. So the data set is the same as before, and what we have done is to be able to have some evidence for those solar neutrinos at a higher significance than those 2 experiments I have talked about. And our result is the most sensitive result among all the xenon time projection chambers in the world. So that's why the announcement about yesterday's announcement was so big. And also the fact that because LZ was able to measure those solar neutrinos via that process that is different than what Ray Davis did, we can do different things. For instance, we can even try to constrain some flux of neutrinos coming from the sun and different other things. I'm going to end with 3 more. I have 3 more slides before I end. One of them is the future for LZ. So LZ has been extremely good at probing the dark matter parameter space. We have world-leading results in high mass WIMP, and we have world-leading result in low mass WIMP. What we want to do is just to continue probing that parameter space, right? We want to be sure that we finish combing the field before we stop. So LZ is going to continue for a few more years until we have collected enough data to continue probing the field, and then we will stop. It will be by the end of 2027 or 2028. In terms of neutrinos and other searches, because of those solar neutrino discovery, with that process, we can probe some supernovae neutrinos, and at the same time, we can continue looking at different other physics processes. So I'm going to end with this summary, which is that dark matter exists. We have so many evidences, but it remains to be found. So we have to know, is dark matter WIMPs? Is dark matter another type of particle? Is dark matter a combination of different types of particle? We don't have an answer for it yet. But in terms of capability in finding what dark matter is, LZ is right now using the best technology in the world to do so, and LZ has been leading, so LZ is well positioned to do it. We are discovery ready. We will continue taking data until 2028. So if you want to be tuned with LZ progress, please follow us on social media. We have a Facebook page, we have a LinkedIn page, and so many other things. And I like to believe that not only LZ effort, but the effort of all those experiments I have shown you before in that world map, trying to look at dark matter, look for dark matter, and finally be able to answer to that fundamental question, what is the nature of dark matter, makes the future of the field bright. Perhaps LZ will find dark matter. If not, a future experiment where LZ and other colleagues will build something bigger will find dark matter, but I'm sure at the end of the day that dark matter will be found because it's somewhere and then it remains to be found. So I will stop here and welcome any question.
Thank you for a lovely presentation and an exciting introduction to dark matter. Tomorrow is the presentation of the Nobel Prize Awards, and so your ties sort of showcasing the potential of dark matter research for a trip to Stockholm is very appropriate. And we wish you and LZ all the best as you try to make that trip. Alrighty, any questions for Dr. Kamaha? Oh, yep, so the question was the goal for the running goal for LZ, how many live days?
Excellent question. So basically, because of the neutrinos that we have discovered, and because of the similarity between neutrinos interaction and dark matter interaction, if we discover so many of them, it will become very hard for LZ to be able to discriminate or differentiate between neutrinos and dark matter. So then the neutrinos at the level where we become too sensitive to them become a natural hindering barrier. We talk in the field about neutrino fog. So our goal then is trying to go as much into probing this white space. I'm showing here with my finger so people on Zoom will not be able to see, but basically trying to probe as much of this space as possible before hitting the neutrino fog. And we know that with 1,000 live days of LZ, we will not reach the neutrino fog. We'll maybe be able to cover only half of this parameter space. Now, remember that we have that natural radioactivity. I have talked about how you can just cut out some distance away from the wall to get rid of some background from the natural radioactivity. But the more you run, the more you collect it, and it becomes even more difficult to cut it and still have a sensible progress. So that one also was factored into account. Does that make sense?
Makes sense, yes.
Okay. I try to not be too sciencey, but okay, maybe a lay person answer will be, LZ is trying to reach 1,000 live days to probe a little bit more into the different theory out there about what dark matter can be. And we'll stop there. Okay?
Other questions?
Yes, you can go ahead.
I guess this is kind of a basic question way back from the very beginning of your program. You start talking about dark matter and galaxies. My question is, I don't remember this from high school, but which direction does a galaxy rotate? Clockwise or counterclockwise?
Excellent question. So which direction? The question is about, we were talking about dark matter inside of galaxies, right? And then which direction are the galaxies rotating? So I like to tell to my student that I always prefer counterclockwise positive, but you can also do counterclockwise negative. At the end, we get the same answer. Basically, what I'm trying to say here is that the direction the galaxy is rotating does not really matter much, because this measurement about some evidence of dark matter based on the rotation of stars inside of the galaxy is basically a measurement that was done on a spiral galaxy, and the spiral galaxy has 2 arms, okay? So you measure based on this arm here, and you also measure based on this arm here. So one of them helps you to cross-check or confirm the result. So if you measure based on this arm here, you will have, for instance, a positive result, and you measure based on this arm here, you have a negative result, but both of them will have the same value, just a positive or negative sign. Does that make sense?
Yeah, the reason why I was asking was just kind of, in layman's terms, just kind of related to high pressure, low pressure weather systems, for example. How low pressure will turn counterclockwise. And that's why I was kind of wondering if galaxies always rotate in one direction or the other.
I don't know. I will have said clockwise. Yeah. So one thing that might be relevant, not the direct, like the sign at which the galaxy is rotating, but the relative rotation of the galaxy is an area in dark matter that, if you think about the Earth rotating around the sun, right, and that there is, for instance, this dark matter source in the universe that has a fixed position, like my left hand. As the Earth is rotating around the sun, and you think about LZ experiment, for instance, located at South to be this way, there will be a time in the year where LZ will be more closer, we have a higher flux of dark matter, and then a time in the year where LZ will have a lower flux of dark matter, right? In that sense, I have thought about discussion, like rotation, not of dark matter itself, but rotation of galaxy, but in terms of the flux of dark matter, right? But not the rotation sign. Does that make sense? Okay. Yes?
As the experiment is happening day after day, what does it look like from a crew standpoint, like in a scientist standpoint, like physically there working on stuff, observing data, sending it to everyone in the world, like on a daily basis?
So a day in the life of a scientist.
Excellent question. So we have like 3 students from LZ here. They can answer better to that question because they actually live that day in the life of the LZ scientist, right?
So where do I begin? So I can start at the beginning of the day. 7 o'clock we go down the cage. We do a coordination talk, a toolbox talk where we talk about the plans for the day. Usually the plans for the day involve either maintenance to specific systems that are needed to operate the detector, or we are doing calibration periods, so specific calibration deployments or source deployments. We will coordinate at that meeting. Well, it's coordinated prior to that, but we will talk about what the plan for that day is. And then we are taking the data during that day as is, and the data just basically comes out of the detector to our data acquisition racks. That pushes it to the surface, and then the surface sends it to California, to NERSC, which is a supercomputer run by the DOE, which then saves and processes all of our data. So on a daily basis, that's happening, and we're just working in the background of that. So it doesn't really see us.
Very good
I hope
question.
that answers your question.
So yeah, so the main thing to remember from George's answer is that the detector is collecting data every single time. As we speak right now, underground, the detector is keep on collecting data. So anytime a particle will pass through, there will be that flash of light and the second flash of light, and that will be recorded in computers that are sent somewhere else to quickly process them and things like that. But we need those fantastic students to be able to go underground and to sometimes look at the data that is coming in if something is obviously wrong, right? To be able to let the crew know, right? And then we can find, we can maybe stop the data acquisition and then fix what is wrong and continue. But if we don't stop, it will continue to take data on and on and on and on and on. Sometimes we do stop on purpose because we want to put those man-made radioactive sources. And to put those man-made radioactive sources, again, we need those fantastic students to sometimes go and take the source from a given location and then put it close to the detector. Question?
Please explain the difference between dark matter and dark energy in a parallel. Has dark energy been proven?
So the question, just to repeat it, asking about the difference between dark energy and dark matter.
Very good question. Can I use you?
Yeah, sure.
Thank you. Okay. So I will touch you, okay?
Yeah.
So, okay. I like to think about, imagine a universe that is only dark energy dominated. I said earlier on that dark energy was that force that caused the universe to expand, right? So we all know about the Big Bang, right? The explosion that happened many, many billion years ago. So, no. I just want you to quickly extend your hand like that.
Okay.
Just do that, right? So a universe that is dark energy dominated, just go like that, right? Without hindrance. But because dark matter is a gravitational force, or a gravitational dark matter is a massive amount of matter that has gravitational force, and gravity tends to clump things together. Then as Jared will try to extend, dark matter will try to basically pull his hand down. So as he's trying to extend, dark matter tries to pull it down, right? So then we have that control expansion rate. I believe that I'm not stronger than you, right? So try to extend your hand, I will try to push it, but you see it's still extending, right? But at a control rate. So dark energy expansion, dark matter contraction, if you want. But because we know from data that the universe is expanding, then we know that dark energy is dominating, right? That's why we have the 70% dark energy, 25% dark matter. But dark matter is kind of controlling that expansion rate. Does that make sense? Thank you, Jared.
Oh, sure. That didn't hurt too bad. Other questions? Actually, I have one quick one.
Yes.
At the beginning of your presentation, you talked about the different ways scientists are looking for dark matter, noble liquids like xenon, but also you mentioned accelerators, you also mentioned satellites. There was a recent splash people may have seen in the news about dark matter and the Fermi satellite. I don't know if there's any comment on that evidence or that paper that was prominent in the news recently.
Very good question. So those space-based detectors trying to look for dark matter are trying to look for dark matter via some decay product, not decay, sorry, annihilation product. So basically, we want to think that dark matter will behave as normal matter. And normal matter, what it has is that to each normal matter, there is an antimatter. And when the normal matter and the antimatter will meet, they will annihilate. And they will annihilate to give you primarily like photons, and those photons will produce some other matter, antimatter, like electron and positron and so forth, right? Now, when we look for those dark matter annihilation product, we look at them in region of space where the background is very difficult to model. So what I'm trying to say here is that you might find an excess, but that excess will not be a true excess. It might be due to a background somewhere that produced that excess, not really a dark matter. I remember in 2013, there was some excess that were found by the Fermi LET at that time, right? And then the community was very excited about it because the excess was significant. But later on, it was found out that to be some neutron pulsars, I think, that were producing those excess of normal matter. So I would say that the background is really key. Understanding all those other particles that can mimic the dark matter is really key, otherwise you are going to be dealing with a false discovery. And more so also for those satellite mission, space-based detectors, because up there, the background is really, really messy. So
Yep.
that's what I recommend on that.
Backgrounds are important. Other questions? Well, let's go ahead and wrap things up and thank Dr. Kamaha again.
Thank you very much one more time for coming out. I really appreciate it, more so given the weather. Thank you.